I know you've been working really hard at it. So I'm incredibly proud of you, and I'm excited to see what you're going to be doing next.
Thank you. Thank you so much, Anna. Mike, do you want to? Okay.
It's still on, but I don't know how to turn it off.
Okay. Oh, sorry. No worries. Oh, it's off. Yeah. Mike. Okay. Okay, I can get started. Thanks, Johanna, for such a nice intro. Hello, everyone. First of all, I would like to thank all of you present, either in person or via Zoom, for taking out the time to be here today. Today, I will be talking about my thesis work on using advanced imaging approaches to characterize degradation modes during fast charging of lithium-ion batteries. Okay. I would like to start with a big picture overview of a world we as human race want to live in. A world with reduced CO2 emissions, a world with reduced global warming, a world that is sustainable and has global energy security. Now, this is a world worth striving for. And mass market adoption of electric vehicles can help make this world a reality. Electric vehicles, or EVs, are a way to provide us with a sustainable future. If you look at this plot, you can see that the life cycle global warming emissions of a mid-sized battery electric vehicle are approximately 50% lower than those from a mid-sized gasoline car, despite the 15% emissions associated with EV manufacturing, because most of this reduction is coming from the operation of the car itself. And in the future, as the electric grid becomes more renewable, these emissions will continue to decline even further. Thus, EVs are a way to provide us with a sustainable future. However, if you own an EV today, you also know that there are many problems associated with it. For example, speed of charging, or availability of public charging stations, or location of charging stations. And among these problems, a top concern faced by EV consumers globally is the speed of charging. For example, if I'm driving my EV from Stanford to LA, I need to think about the charging stations to stop at on this journey. But more importantly, I need to factor in the charging time of my EV on this already long 7-hour journey. The speed of charging is preventing consumers from buying EVs, and their sales remain low despite government incentives. And a potential solution towards that problem is extreme fast charging, or XFC, of EV batteries, which is to make charging an EV similar to fueling up your gasoline car at a gas station. Now, if you look at this data, you can see that Tesla Supercharger offers the least time to charge for 200 miles as compared to the other state-of-the-art chargers available in the market today. And it still takes approximately 30 minutes to charge for 200 miles. Thus, US Department of Energy and US Advanced Battery Consortium has identified extreme fast charging as one of their top priorities to reduce lithium-ion battery times to less than 10 to 15 minutes to meet their national goal of around 50% plug-in electric vehicles in the United States by 2030. Now, this is a very lofty goal in a very short period of time, and especially because the present-day lithium-ion battery technology cannot achieve this goal without a significant reduction in the capacity of the battery over cycling, thus reducing its battery lifetime significantly. Now, let's look into how a lithium-ion battery works and why is it difficult to fast charge it. Here, I'm showing a schematic of a lithium-ion battery that consists of a positive electrode, lithium conducting electrolyte separator, and a negative electrode. Now, during battery charging, what we are doing is we are moving lithium ions from the positive electrode through the electrolyte and separator towards the negative electrode, which is made of carbon. And then these lithium ions, they start intercalating between these layers of graphite in the form of stored electrochemical energy. Now, when you discharge your battery, you're moving lithium ions back from the negative electrode to the positive electrode. Now, what happens when we try to fast charge a battery? What we are doing is we are moving these lithium ions really fast from the positive electrode to the negative electrode. And these ions, instead of intercalating between these layers of graphite, they start accumulating on the surface of the battery anode, triggering an electrochemical reaction known as lithium plating. Lithium plating is one of the key XFC failure pathways. Here, I'm showing two custom-made battery pouch cells that were charged between 10 and 15 minutes, and both of them experienced deposition of this whitish material on the surface of the battery anode. This white material is lithium metal, and this process is lithium metal plating, which is given by equation 2 here. Now, what happens at high charging rates is that lithium metal plating becomes favorable over lithium intercalation. And lithium ions, instead of intercalating between the layers of graphite, they start plating as lithium metal on the surface of the battery anode. And if we look closely at the electrochemical potentials of the two reactions, you can see that they are pretty close to each other, and hence the competition between the two reactions. And fast charging creates favorable conditions for lithium plating to dominate. And once the battery is cycled from, let's say, 0 to 450 cycles, it experiences significant capacity fade over cycling. Lithium plating is still not completely understood in the research community due to its very complex mechanisms. And in order for us to develop fast charge batteries for EVs, we need to understand this electrochemical reaction at a fundamental level. And therefore, in my thesis, I focused on understanding where does lithium plate and how does it progress on the battery anode during XFC in lithium-ion batteries. Particularly, my thesis focused on investigating 3D morphological evolution of plated lithium during fast charging. Now, why understanding morphology of lithium plating is so important, and especially in 3D? If you look at the schematic, you can see that plated lithium is hypothesized to start or initiate at this graphite separator interface, and then it forms these structures that grow through the separator, leading to battery short circuit at some point. Now, understanding morphology is important because it can give us information about the shape, size of these structures to understand how do they grow. What is the mechanism of battery failure? For example, do they form these sharp tip-like features that poke holes through the separator, causing battery short circuit? Or are they these flat, root-growing, mossy structures that cover the entire circumference of the graphite electrode, blocking lithium intercalation? In addition to understanding morphology, my thesis focused on understanding 3D spatial heterogeneities of dead versus active lithium during fast charging. Now, what is dead and what is active lithium? If you look at the schematic, you can see that we have active lithium, which is reversibly plated. This lithium has an electronic pathway open to it, which means it can accept an electron, intercalate into the graphite, and find a pathway back to the NMC cathode during the battery discharge process. Thus, this lithium does not cause capacity fade of the battery. However, dead lithium is the one that is irreversibly plated. As you can see from the direction of this arrow, this lithium has no electronic pathway open to it to intercalate into graphite and go back to the cathode during the discharge process. And dead lithium is the one that is associated with battery capacity fade during fast charging. Therefore, understanding the 3D morphological behavior and heterogeneities of dead lithium and differentiating them from those of active lithium is essential to developing an improved understanding of how lithium plating causes battery failure during fast charging. Numerous methods have characterized lithium plating because it's a very important and timely topic, so a lot of attention is being given to it. But for the sake of this talk today, I have summarized 4 important studies that, in my opinion, have significantly advanced our understanding of lithium plating and laid the foundation for my thesis work. First study was led by SLAC scientists, in which they employed in situ X-ray diffraction to create 2-dimensional mapping of plated lithium in these industry-relevant pouch cells. Their data demonstrated the spatial heterogeneities of lithium plating span in X and Y direction, so laterally. But as you can see, this study was limited to 2D, and translating it to 3 dimensions is very difficult. In addition, this study was limited to millimeter scale resolution. Second study was led by scientists at NREL who employed operando X-ray diffraction to investigate spatial dynamics of lithium plating. Their data showed that spatial heterogeneities of lithium plating also span as a function of depth of the graphite electrode, which is great. However, this study is limited to 1D. and morphological information was missing from both these studies. And that's where the gap was bridged by another study conducted by scientists at UC Berkeley and LBNL, in which they did in situ three-dimensional X-ray imaging to create 3D mapping of lithium plating. And this work showed that how this layer of mossy lithium leads to underlithiated graphite particles underneath. However, this study was limited to a half cell, as you can see here, in which lithium metal is used as an electrode on the other side, which is an infinite source of lithium. Fourth study was conducted by scientists at UChicago and Argonne National Lab, and it has just come out. And these scientists developed an analytical approach based on scanning electron microscopy and FibSEM to differentiate active lithium from these inactive or dead lithium deposits. This is an SEM image of lithium dendrite. It does give us morphological information, as you can see, but this is only surface information. They were able to create these three-dimensional image using FibSEM, but we know that sample cross-sections for FibSEM are obtained through destructive ion milling. Thus, in situ three-dimensional characterization of lithium plating in full-cell lithium-ion batteries has been missing from literature. And it is important to study because battery is a very complex electrochemical device. It continues to be electrochemically and chemically active even after cycling has stopped. And when you try to open this battery, there could be a potential physical damage to the battery anode or cathode and or the separator, leading to incorrect data. And thirdly, two-dimensional information, if used alone, can be misleading. Here, I'm showing a schematic of a lithium-ion battery that consists of copper and aluminum current collectors, graphite anode, transition metal or NMC cathode, separator, and this graphite separator interface. Now, lithium plating is hypothesized to start plating in this interface and then form these structures that grow through the separator. Now, it is extremely challenging to understand the morphological behavior and spatial heterogeneities of lithium plating in 3 dimensions in situ in a full cell battery, because visualizing this interface non-destructively in a full cell battery in 3D is a challenge in itself, especially at these micron relevant length scales. Now, to address this challenge, my approach involved using non-destructive advanced neutron and X-ray imaging diagnostics. Neutron and X-ray 3D imaging is particularly advantageous for this work because of the way they interact with matter, which is encapsulated by this Beer-Lambert's law. Here, I is the beam intensity through the sample, I naught is the incident beam intensity, T is the neutron and X-ray path length through the sample, and mu is the linear attenuation coefficient, which is a materials property, which means this number would be different for different materials. Now, for neutrons, this mu is directly proportional to sigma total, which is a total neutron cross-section. It is a summation of coherent scattering, incoherent scattering, and absorption. Now, let's look at this table. You can see that its value for lithium is very high and that for graphite is low. Thus, neutrons are very sensitive to detecting low Z materials such as lithium, especially on graphite because of the relative neutron contrast of the two materials with respect to each other. Now, if you look at the X-ray side, you can see that mu is directly proportional to mu m, which is a mass attenuation coefficient. Like neutrons, it's a summation of coherent, incoherent scattering, and absorption. And if we look at the right side of the table, you can see that its value for copper is pretty high, which means X-rays are sensitive to high Z materials such as copper. Thus, we can use the sensitivity of neutrons to lithium and X-rays to high Z materials such as copper to detect lithium on graphite in situ in a full cell battery. Thus, my thesis work focused on first establishing the feasibility of simultaneous neutron and X-ray tomography for XC2 battery diagnostics. Then I used learnings from this work to design a neutron-friendly battery for in situ or operando detection of lithium plating during fast charging. And thirdly, I used my developed battery to investigate the proposed fundamental questions about lithium plating during fast charging. Now, let's get started with the technique development work in which I focused on using simultaneous neutron and X-ray imaging, or NEXT. NEXT is a non-destructive 3-dimensional imaging modality that provides us dual information by the interaction of the two probes with matter, because we are combining the strength of neutrons for lithium and X-rays for high Z materials such as copper. I performed these experiments at a BT2 imaging beamline at NIST Center for Neutron Research. A schematic of the beamline is shown here. In this schematic, you can see that red is the neutron beam, which is produced by a nuclear reactor. Blue is the X-ray beam, which is produced by a microfocused laboratory-based X-ray source. Now, these two beams hit the sample at the same time here during the imaging experiment, and they are perpendicular to each other. And then we have a neutron and an X-ray detector that detects the neutrons and X-rays after they have interacted with the sample, providing us a neutron and an X-ray image. My design of experiments for this work included a single-layer battery pouch cell that was assembled by scientists at Argonne National Lab. This pouch cell consisted of a graphite anode, NMC cathode, cell guard separator, and liquid electrolyte. And this battery was charged at 9C, which is around 10 minutes of charging for 450 cycles. When I opened the battery, I saw these whitish deposits, which correspond to plated lithium. And then I cut a strip around this blue dotted rectangle here. I cut a strip because it's very difficult to 3D image a full flat pouch cell. And then the strip was put in a glass capillary, which was then used for the next experiment. Here, I would like to note that during sample prep, lithium was exposed to moisture in the air. And because lithium is so reactive, it formed lithium hydroxide. So any lithium-containing protrusion that I would be showing in this work is lithium hydroxide. Let's look at the 2D or top view or XY grayscale neutron and X-ray images of first the pristine graphite strip and second the XFC cycled strip. These are the neutron and X-ray images of pristine graphite. Here, the outer circle corresponds to glass capillary that was used to house the sample. And in the neutron image, we can see one strip, which means we cannot differentiate between graphite and copper, right? But in the X-ray data, we can see this copper strip pretty clearly. This makes sense because X-rays are more attenuating to high Z materials, such as copper. In addition, we can see these dark streaks coming off the end of the copper, which are beam hardening artifacts. Now let's look at the data for the XFC cycle electrode. Here we are looking at the outer glass capillary as well, and then we are looking at this graphite anode, which is clearly visible in the neutron images, but not so in the X-ray data. In the X-ray data, again, we can see copper pretty clearly. Thus, we can use the information from this neutron and X-ray image to create a two-dimensional histogram for an improved segmentation, which I'll show you on the next slide. So my neutron image gave me this neutron histogram, which shows two peaks. My X-ray image of the pristine graphite gave me my X-ray histogram. Now the x-axis of this X-ray histogram is longer, as you would see here, as compared to that of the neutron histogram. Therefore, these peaks appear stretched. Then I use this, combine this data to create this two-dimensional histogram. Here on the x-axis, we have neutron gray level values. On the y-axis, we have X-ray gray level values. The negative pixels on each of these axes were assigned to background. Then this peak at the top was assigned to copper. Why? Because copper is more attenuating in X-rays than graphite. And then this peak was assigned to pristine graphite. Now, a way to look at the quality of segmentation is to look at spatially their location in a colorized segmented image. And if you look at this colorized segmented image, you can see that copper and graphite are on top of each other and they're flat. So this means this is a good quality segmentation. Next, I used the same developed framework to segment different battery materials in my XFC cycled anode. Here, I used data from my neutron histogram and my X-ray histograms at the bottom of the slide to identify these materials in this 2D bivariate histogram, where background pixels were assigned and then copper and cycled graphite. Now let's look at the colorized image of the XFC cycled graphite, where you can see delamination of the copper current collector from the cycled graphite. We can also see this giant lithium-containing protrusion evidently beneath this white dotted circle. Now these are 2D images of a 3D volume. Then I stitched them together to look at the depth of graphite electrode degradation. Here I'm showing 3D visualization of pristine electrode, where yellow corresponds to copper current collector and pink corresponds to graphite. And both these strips are on top of each other with no sign of lithium plating. However, if you look at a 3D visualization of XFC cycle electrode, we can see some of the delamination and we can see this giant lithium containing protrusion very clearly, which can be directly correlated to this brightish deposit on the optical image of the graphite strip. Now, this is 3D data. We can correlate this 3D visualization to certain regions along the length of this graphite strip. For example, slice A here, which is the top view XY slice, is directly correlated to thick yellow line labeled A and white yellow line labeled A on the either side. Same is true for slice number B. In slice C, we can see this lithium containing protrusion very clearly, which can be directly correlated to thick yellow line labeled C and white line labeled C on the either side. Now, if we move away from this protrusion, for example, in slice E, we can see no protrusion, and we can see this graphite pretty close to copper current collector, which can be correlated to thick yellow and white lines labeled E on either side. Thus, to summarize, in this work, I established the feasibility of simultaneous neutron and X-ray tomography for ex situ 3D battery diagnostics. In addition, this work demonstrated qualitative correlation between electrode degradation and lithium plating. However, you would notice that this work was done in ex situ, which means I opened the battery, cut a strip, and then imaged it. However, to answer the proposed questions, we need to carry out in situ imaging. And this work made me realize that in order to carry out in situ imaging, I need to design a neutron-friendly battery to leverage high-resolution imaging for lithium plating detection, which is what I did in my next project. Now, what is a neutron-friendly battery? This battery satisfies dual criteria from two scientific disciplines. First, electrochemistry and neutron imaging. From electrochemistry perspective, the battery should have XFC cycling capability. The battery should also be able to undergo extended XFC cycling so that I can detect lithium plating. And any chemical modifications I make in the battery should allow compatibility with the battery electrolytes and especially metallic lithium, because lithium is so reactive and we have to be safe. Now, from neutron imaging perspective, the battery should allow easier detection of plated lithium at the graphite separator interface. It should allow higher signal to noise ratio so that I can detect lithium with good statistics, right? It should also ideally allow high throughput battery imaging. Now, my previous work made me realize that each neutron tomography scan takes several hours to complete. So if we can stack these multiple batteries on top of each other, we can collect data in just one imaging experiment. Now, neutron imaging defines the design criteria for this battery. Let's look at the total neutron cross-section. Now, if you recall, this neutron cross-section for lithium is pretty high. So for us to be able to distinguish lithium from other battery materials, we need to replace other battery materials that have high neutron cross-section with those that have low neutron cross-section. Another important criteria is expected neutron transmission. This is Beer-Lambert's law, and here I over I naught is the expected neutron transmission, which you would see that does take into account mu, which is linear attenuation coefficient, and which is related to sigma total. But it also takes into account neutron path length through the sample. Thus, we have to replace the battery materials that offer low transmission with materials that offer high transmission so that we can distinguish lithium from the other battery components in situ in a full cell battery. Thus, to make a battery neutron friendly, we have to use materials that offer high neutron transmission and have low neutron cross-section. Now, keeping these design criteria in mind, I developed design principles. Now, let's look at some of the actual battery materials. Here you can see hydrogen has a significantly high value for sigma total, and so does iron. And hydrogen is present everywhere in the battery, in organic electrolytes, in the hydrogenous battery separator. So in order to make a battery neutron friendly, we have to replace hydrogen with deuterium or fluorine and iron with aluminum-based materials. Thus, the first modification I made in my battery was replace a hydrogenous battery electrolyte with a deuterated electrolyte. And you can see here, this increased the transmission significantly through the battery. Next, I replaced a polypropylene, which has a significant hydrogen content, with a fluorinated polymer. And again, we have a significantly higher neutron transmission. Next, I replaced the standard cell guard separator, which is made of polypropylene, polyethylene, again, very high hydrogen content, with fluorinated polymer, which increased transmission through the battery. Next, I replaced the stainless steel spacers, which are physically placed very close to the graphite anode and the separator. So I replaced them with aluminum-based materials to increase transmission from my region of interest. And lastly, I made my electrodes really small. And by small, what I mean is I decreased their diameter, which means the neutron path length, or T, decreased significantly, which increased the transmission. Thus, to summarize, all these modifications made my battery neutron friendly, the final design of which is shown here. Now, this design is based on a 20xx format coin cell with the modifications I just talked about: fluorinated gasket, custom aluminum spring, copper-coated aluminum spacer. My electrodes are small and neutron-friendly separator. Now, to revisit the electrodes, you can see that this T is the diameter, which is a neutron path length. So you can see from the Beer-Lambert's law how making them small increases transmission from the battery. Now, here I would like to mention that a coin cell geometry is particularly advantageous for neutron tomography, because this geometry results in uniform attenuation throughout the scan, thus resulting in less imaging artifacts. In addition, these coin cells are pretty small, so you can stack a lot of them on top of each other for each neutron tomography scan. And they also reduce the use of expensive deuterated chemicals. So you can make a lot of coin cells with a very small volume of expensive chemical. Next, I tested the electrochemical performance of my battery. So here I'll be showing you the performance of my battery in comparison to a standard battery. Now let's see how do these batteries perform in slow cycling, which is at C/10 or C/2, which is a very low current, if you look here. So here I'm showing potential and current versus time plot. And as you can see, these batteries cycle between 3 and 4.1 volts. Now let's compare the electrochemical signature of my developed battery. You would notice that these two signatures look pretty similar to each other, which means that my battery performed okay under slow cycling. Now let's see how does the battery perform under fast cycling at 6C, which is 10 minutes of charging. And by 10 minutes, you would notice here the current relative to the current given in slow charging is pretty high. So this battery was cycled between 3 and 4.1 volts at 6C and then discharged at C/2. And this signature corresponds to that of a standard battery. Now let's compare the signature of my neutron-friendly battery. Again, the two signatures look very similar to each other, which means that my battery is capable of fast charging at 6C. And once I was content with the electrochemical performance of my battery, I proceeded with the neutron transmission results at MIT Nuclear Research Lab, Oak Ridge National Lab, and Paul Scherrer Institute. In this picture, you can see that multiple coin cells were stacked on top of each other for the experiment, which is high throughput imaging. This is a neutron image of a standard battery, which is completely opaque. You can see by comparison, the neutron image of my battery did increase transmission significantly in these regions. Now, this was a result of fluorinated gasket and deuterated electrolyte. But you would notice that the stainless steel spacer is blocking my region of interest, and we cannot see the interface. And therefore, in my final design, when I replaced the stainless steel spacer with an aluminum-based material, I could see my, my region of interest, which is very clearly visible in this high-resolution image collected at PSI. Thus, to summarize, in this work, I developed a neutron-friendly battery for in situ or operando detection of lithium plating during fast charging. This battery is capable of fast charging at 6C, and the battery exhibited excellent neutron transmission, enabling in situ non-destructive visualization of this graphite separator interface in a full cell battery. Then I used my developed battery to investigate the fundamental questions about lithium plating during fast charging. Particularly, I investigated 3D morphological behavior and spatial heterogeneities of dead versus active lithium during fast charging. In this work, I asked, how does the 2D and 3D morphological behavior of lithium plating evolve during fast charging? And is there a correlation between the 3D spatial heterogeneity of dead versus active lithium and regions of the graphite anode that form more dead lithium as compared to the other regions? And if there is a correlation, where are the regions that form dendrites, which degrade battery performance? Now, to address these scientific questions, I conducted high-resolution 3D neutron tomography at Icon Beamline at the Paul Scherrer Institute in Switzerland. This is a schematic of my neutron-friendly battery, where Z corresponds to thickness of the graphite electrode or the distance through the battery. And XY corresponds to the top view plane. Now let's keep that in mind when we look at the 3D data. Here I stacked two batteries on top of each other as I collected 2D images of a 3D volume, and the stack rotated from 0 to 360 degrees. Here I explored two charging rates, 1C and 6C, where 6C corresponds to a relatively faster charging rate as compared to 1C. My pixel size was 5.7 microns and spatial resolution was around 10 to 15 microns. Now this is important because I mentioned the relevant length scales earlier in my talk. So this resolution meant that I was able to detect lithium micron scale deposits in a full cell battery. And the data was collected of the batteries in the charged and then in the discharged state. Now, before we look into the data, let's revisit the schematic of the battery and see where different battery components are physically located. So in this battery, we have a copper current collector, and then graphite anode, then we have separator, and we have NMC cathode. Now let's look at the cross-sectional XY, XZ, and YZ images. In these images, we can see this line corresponds to the separator. Anode is on the top, and then NMC cathode at the bottom. And we see these brightish clusters on the side of the graphite anode in this cross-section XZ image, which correspond to lithium deposits. This cluster in the YZ cross-sectional image also belongs to lithium deposit, which we can see very clearly in this top view or XY video. Now, in this video, we are going from the copper current collector towards the cathode. These brightish deposits, as you can see, they are at and around the edges of the graphite anode, which means those are the regions that are most susceptible to forming lithium. Now we will start seeing this graphite anode in the middle. We have also started seeing this separator. Separator is a very thin membrane, which is usually placed very flat during battery making, but its undulating surfaces or some crevices do get picked up in a micron scale imaging, which we can see in the form of these structures in this image. And this brightish cluster you can see corresponds to plated lithium. Now we are going on the other side of the separator, and we'll start seeing this NMC cathode as a round, punched, big disk. Okay, this data clearly shows in situ 3D observation of dead lithium on, excuse me, on graphite in a full cell battery. Now let's look at the 2D top view or XY neutron slices that reveal different morphological behavior of plated, dead, and active lithium at 1C versus 6C. But first, how was I able to differentiate these three forms of metallic lithium in my battery in the first place? As I just mentioned, I collected data in the charged and the discharged state. So any lithium in the battery in the charged state corresponds to plated lithium. And the residual lithium in the battery in the discharge state corresponds to dead lithium. It is dead because it's irreversibly plated. It had a chance to go back to the cathode, but it didn't. So it stayed there, it became dead. And these two were measured. Then I subtracted my 3D data of the charge from the discharge tomography to get a calculated subtracted data set, which gave me my active lithium. This is the lithium that went back to the cathode during the discharge process. Now let's look at the images. You would see in these images brightish deposits around the edges of the graphite electrode at 1C. Now, if we compare this data with that of a 6C, you can see a clear morphological difference. For example, at 6C first, qualitatively, we are looking at a more complete circle, which shows that qualitatively there's higher amount of plated lithium than at 1C, which is expected. We are also seeing this mossier, more isolated and denser deposits as compared to at 1C. Now, in addition to these morphological differences, there are also some similarities in lithium plating behavior between both the charging rates. For example, there are regions of the graphite that formed more dead and active lithium, plated and dead lithium, as compared to other regions that formed less plated and dead lithium. And these regions are present in both the charging rates. So this finding suggests that there are spatial heterogeneities in the behavior of lithium plating, which is in agreement with the study by Slack and NREL scientists. Now let's look at these spatial heterogeneities in 3 planes in 2D, XY, XZ, and YZ. But before we do that, let's revisit the battery schematic. We have a current collector, graphite anode, interface separator, and NMC. And this is the corresponding cross-sectional XZ image of the battery, where we have anode at top and cathode at bottom, and separator in the middle. Now, I only used data that corresponds to this slices corresponding to the blue rectangle here, because lithium is only plating at the interface, and that's what I care about, right? Here I'm showing the cropped grayscale image of my battery with the colorized segmented pink regions. They are corresponding to plated lithium. Here, region number 1 is near the current collector. Region number 2 is mid graphite. Region 3 is the interface, and region 4 is the separator. Now, I investigated the 3D spatial heterogeneities at all these 4 different regions because it can tell me the direction in which lithium is plating in 3D. Now, let's look at the data in the X, Z, and YZ planes, which are cross-sectional views. If you look at this data, you would notice that lithium is plating mostly on the edges of the graphite anode at both the charging rates. This is a similarity. But you would also notice that this plated lithium is mostly present in high amounts in the separator or near the interface, as compared to near the current collector. Now, if we compare these images with those of dead lithium, you would notice that not all the plated lithium became dead. For example, let's focus at this blob in the cross-sectional XYZ image at 1C and compare that to the blob of plated lithium. This is much bigger than this, which means most of the lithium near the current collector went back to the cathode during the discharge process. However, mostly lithium at the interface and in the separator is the one that became dead. Now, this finding relates to the finding of active lithium, where you can see these deposits are mostly near the current collector. However, in the separator, we don't see a much active lithium, which means that lithium mostly becomes dead or irreversibly plated in the separator and in the interface, whereas lithium near the current collector has an electronic pathway open to it to find its way back in the battery. That's my hypothesis. Now let's correlate these cross-sectional images to the top view or XY images. Now first, near the current collector, we can see that at 6C, we have a lot of plated lithium as compared to 1C. Same is true for dead lithium. You would also notice that the regions that induced most plated lithium are the ones that formed more dead lithium. Regions that formed less plated lithium are the ones that formed less dead lithium. So this shows spatial heterogeneity in the formation of plated lithium in all the X, Y, and Z dimensions. Now, if you look at the near the so sorry, it had stopped working. Okay, so sorry about that. Now, if you look at the second region, which is mid-graphite, you would notice that at 1C, we are looking at higher amount of plated lithium as compared to near the current collector. We also see that regions that formed most dead lithium at both 1 and 6C are the ones that formed more dead lithium. Same is true for regions that formed less plated lithium are the ones that formed less dead lithium. Now, if we look at this interface, we notice these crescent moon-like geometries that are present at 1C and also at 6C. Spatial heterogeneities are also again observed at this region as well. But in addition, we also started seeing these tip-growing growths that are appearing at the interface at 6C. Now, in the separator, these tip-growing growths are more evident at 6C. However, by comparison, if you look at 1C, we didn't observe any tip growths. We only observed this mossy root-growing morphology in a crescent moon-like geometry. You would also notice one thing, that active lithium is the highest near the current collector and lowest in the separator, which is in agreement with what we observe in the cross-sectional images. Now let's look at the 3D visualizations of plated dead and active lithium at 1C. By looking at these visualizations, you would notice that there are regions that didn't form any dead lithium. There are regions that formed a lot of dead lithium. There's also mossy nature of this morphology. By comparison, at 6C in plated lithium, we are seeing a more complete circle. We also see that this plated lithium has porosity associated with it. For example, there are nodules which are much denser as compared to the other nodules that are less dense. So this plated and dead lithium has varying density and porosity associated with it. At 6C, we also notice these tip growths, which are originating from the base of the root growing structure, which we didn't observe at 1C. Now, if we look at the dead and active lithium placed on top of each other in 3D, you can see that there are similar spatial heterogeneities in the behavior of lithium plating at both the charging rates. For example, first, there are regions that didn't form any dead lithium present at both 1C and 6C. There are regions that formed very low active lithium. We mostly see red here, right, which is dead lithium. And this is present in both the batteries. We see regions that formed very high active lithium present in both the batteries. So there are similar spatial heterogeneities. However, there are different morphological growth mechanisms of plated lithium at 6C versus 1C. For example, at 6C, we do see these sharp tip growing features that seem to be propagating towards the center of the graphite anode. However, at 1C, we see this mossy root growing structure, which seems to be propagating outwards away from this structure. Now, the known mechanism of battery failure caused by lithium plating is that lithium plating initiates at the interface and then forms structures that grow through the separator. My work has shown that it's much more complicated than that. Lithium might have most probably have initiated at this interface, but then it grows towards the copper current collector, towards the center of the graphite anode, and in the separator in the form of these deposits with different morphology at 6C. Whereas lithium near the current collector has a way to intercalate into the graphite, leaving behind these irreversibly plated or dead lithium deposits, which cause capacity fade of the battery. Now, in the future, I'm curious to know, would these tip growing structures continue to grow towards the center of the graphite anode at 6C, leading to a completely blocked lithium intercalation? So battery wouldn't short, but it would have a significantly lost capacity that it wouldn't work, which is a form of battery failure. Or would these tip growing structures fully penetrate the separator at 6C, leading to battery short circuit? Which one of them would happen first, or would they happen concurrently? In addition, at 1C, we observed mostly this crescent moon-like geometry of mossy lithium. I'm curious to know, would those clusters grow towards the center of the graphite anode and cover the entire circumference? Or tip growing clusters would also be observed at 6C if we continue cycling the battery. So these are the 4 potential questions that my work can lead to, and hopefully they can further shed light on the growth mechanism of lithium plating and how it causes battery failure. But now the question is that, and it's important to do so operando while the battery is cycling. And now the question is that, given the data that I have shown today and the information we have available, how can we design a fast charge battery? My work has shown that lithium plates at these regions where some of it is active and reintercalates into the graphite, and some of it becomes dead. Now, the first idea that I have is, can we explore the interplay between graphite electrode thickness and the optimal XFC cycling protocol, especially when our colleagues from the Stanford Material Science Department have recently shown that dead lithium can be brought back from dead. It can be made alive because it's so responsive to battery operations, especially to the stimulation of electric field. So can we use the information shown by my work in 3 dimensions with that work to explore this space of optimizing graphite thickness and XFC cycling protocol in an actual battery in an electric car? Second, my work has shown that area around the edges of the graphite is most prone to lithium plating. So can we use tools from interfacial chemistry to develop lithophilic coatings that promote or facilitate uniform lithium plating and deposition? Third, the edges of the graphite anode were the most prone to forming lithium. Can we use 3D manufacturing to tailor the design of these edges so that we can reduce their intrinsic surface heterogeneities, such as porosity, tortuosity, what have you, which has been reported in literature to induce preferential metallic lithium nucleation? Now, these are the three potential avenues where my work can contribute to helping us design a fast charge battery today. Thus, to summarize, in this work, I have conducted in situ 3D non-destructive detection of lithium plating on graphite in a full cell battery. My work has shown 3D spatial heterogeneities in the behavior of plated, dead, and active lithium at 1C versus 6C. And simultaneously, the work also showed different morphological growth mechanisms of lithium plating and how do they propagate under fast charging. Now, I hope with my work, I have convinced you that I answered where does lithium plate and how does it progress on the battery anode during fast charging in lithium-ion batteries. To summarize, first, I established the feasibility of simultaneous neutron and X-ray tomography as an advanced characterization method for XC2 battery diagnostics. Second, I developed a neutron-friendly battery that is capable of fast charging and enabled us to visualize graphite separator interface in situ in a full cell battery. Then I used my developed battery to investigate 3D morphological behavior of lithium plating, where my work has shown that lithium plating growth mechanism in a real battery is much more complicated than what we know already, where these deposits are left behind and lead to capacity fade of the battery. I envision that findings from my work will help us design better 3D graphite anode architectures that minimize lithium plating during fast charging. But in addition to that, I also believe that my technique and battery development work can contribute to the development of emerging battery technologies such as solid-state batteries or anode-free batteries that would have a long cycle life and can be fast charged for mass market adoption of electric vehicles globally. With this, I would like to thank my PhD advisors, Professor Tony at UC Boulder, Dr. Becker at SLAC National Accelerator Laboratory, my reading committee, Professor Howe from Stanford EE, Professor Bao from Stanford CAMI, Professor Pianeda from Stanford EE, and special thanks to Professor Murray and Professor Fair for serving on my defense committee. I would also like to thank Dr. Lama from NIST Center of Neutron Research for teaching me everything I know about neutron imaging. Next, I have a very long list of scientists and collaborators and colleagues to thank from several national and international research labs, to all the Tony and Becker group members at SLAC and UC Boulder, to the neutron imaging scientists at NIST Center for Neutron Research, to the scientists at Argonne National Lab for synthesizing the battery electrodes used in all my thesis work, to the battery scientists at Idaho National Lab for cycling my pouch cells, to the battery scientists at NREL for inspiring the design of my neutron-friendly battery with their X-ray-friendly battery design, to all the neutron imaging scientists at Oak Ridge National Lab for taking my neutron transmission results and for their support, to the computational imaging scientists at Brookhaven National Lab for helping me implement their developed mathematical algorithms within the framework of my imaging framework, to the Neutron Imaging and Applied Materials group at Paul Scherrer Institute, without whom the last piece of this work would never be possible, to Professor Wood's group and her group for their kindness and generosity shown when NIST shut down unexpectedly in 2021 and doing the PSI beam times with me. Next, I have to thank my funding support from Diversifying Academia Recruiting Excellence Fellowship at Stanford, Schlumberger Faculty for the Future Fellowship, and most recently, the ECS Edward G. Weston Fellowship. My publications to date are the following, and with this, to a sustainable future of electric mobility. And I'm happy to take any questions you may have. Thank you.